Without further ado, I'd like to introduce Dino Dai Zovi. Dai Zovi. I thought I would mess that up. To some of us, he's a bit of a cult hero for a number of reasons. First and foremost, he has a new book out, which is entitled The Mac Hacker's Handbook, Wiley, 2009. And it's small, but packs a pretty good punch. Starting with a good architectural introduction to many of the things he's going to talk about today, finishing with specific examples of each one. And much to my delight as a reader, it's nicely indexed, so I can't recommend the book highly enough. He is a winner of several famed hacking contests which have won him distinct notoriety. Notably, at CanSec West, they had a Hack This Mac contest, which he won remotely. Gave his exploit to a friend. His friend successfully ran the exploit, won the Macintosh that was there, the notebook that was, or MacBook that was there for the taking for winning the contest. And more importantly than that, he got the actual money from the contest, which was significant. And
$10,000 for a night's work, isn't it?
Yeah, 10K for a night's work. So what we're about to experience in this session is indeed a product of that sort of experience. Probably most importantly, he got blogged as one of the top 10 sexiest geeks. Yeah, absolutely, absolutely. So without further ado, I'm looking forward to hearing this session as well. Let's welcome Dino.
Thank you, Matt. Thanks for the great introduction. Now I know why you all are really here. Okay, so this talk is going to be somewhat low level and somewhat technical, so I'm going to kind of do a little drill down on review of a lot of kind of how Mach works before I get into the goodies, but I'll try and keep demos going to keep everyone awake. So let's get into the fun. So I'm going to talk about kind of the relationship between OS X and Mach, and especially why this is a good place to do rootkit techniques and good stuff to use. And then I'm going to go kind of talk a little bit about some userland techniques and then basically work my way to the kernel. So first, let's discuss what is Mach. We have our sort of big OS X kind of system architecture diagram, and this is cleverly stolen from Wikipedia, and I just didn't bother to even zoom in on the important part, which is kind of in the lower half there where it shows the kernel, which is called XNew. So XNew is a hybrid kernel between the Mach microkernel and the FreeBSD kernel. So essentially you have what they did is they took the kind of the Unix personality from FreeBSD and ported it to the Mach microkernel. And so essentially they wrote all the system calls and all that stuff is implemented on top of Mach. But you can still get direct access to Mach, and this is sort of the place that we'll be playing. So better way to understand this is, sup dog, we heard you like kernels. So we put a kernel in your microkernel so you can Mach while you BSD. So like I said, basically, XNew is this kind of dual personality kernel, and it has sort of a number of the usual kind of surfaces that you'd expect on any Unix-like system. That's the Unix system calls. It's a BSD-derived system, so we have sysctls and sort of that whole bag of stuff. However, what makes it different is a lot of the kernel services are implemented as in-kernel RPC servers. So there are system calls to Mach, like direct index by number, like a system call table, like a Unix and Windows system. However, there's really only like 10 of them. So it's a microkernel. It's really small. And all the communication that you do with Mach is actually over remote procedure calls. And so what the system calls let you do is basically just let you send a message, and the kernel just routes the message. And I'll talk a little bit more about what you can do with these RPC services, but it's sort of an interesting interface where, if you're like auditing the kernel for like memory corruption bugs, nine out of 10 people just scan through the system call table and fuzz those, that only covers maybe 80% of the kernel attack surface. The other 20% are all over Mach RPC, and there were some easy bugs there. I mean, like, oh, there's an integer. Let's pass a -1. Crash. That code really hasn't been touched much since like 1994. So it's it's like going back in time. So to understand some of the things that we'll be talking about, need to kind of go over a lot of the sort of the Mach abstractions, because these are pretty unfamiliar unless you happened to just get out of college and Avi Tannenbaum was like your professor. No one else really talks about these. So what Mach does is Mach's main abstraction is the task. And a task is basically just a resource container that has the address space, the virtual memory maps, and all the pages in it. It has one or more threads that actually perform computation, and it has what's called an IPC space, IPC for inter-process communication. And what that is, that space includes basically what are called port names and port rights, which I'll somewhat gray area that I'll get into in a little while. A thread, we all know what a thread is. And the big thing is what's called a port. A port is the main communication abstraction in the Mach kernel. And the best way to think of this is it's like a mailbox, like a restricted sender PO box. Basically, one task can own receive rights to a port. It's the only one that can actually receive messages on it. However, it can grant rights to send messages to that port. And it can be many senders, only one receiver. However, a task cannot send messages to the port unless it's been granted this right specifically. And what's called the Mach message is the unit of data communication between ports. And these are structured, ordered messages. Unlike Unix, where basically just about everything is a sequenced byte stream, sockets, pipes, all that's how they do things. Mach actually uses higher level structured messages. And they're reliable. They don't get lost. They're sequenced. So it's kind of like TCP in that regard. So port names and port rights are kind of another crucial thing to understand. And they're kind of easy to understand if you think about them like Unix file descriptors. I assume most of us kind of know how file descriptors work, or Windows handles. A port name is just a 32-bit task-specific number that refers to that port. So it's just like a handle or a file descriptor. Even though two different tasks may have the same integer that refers to a port, it's not necessarily the same port. It's just only meaningful in that task. And each of those task names have a series of rights. And so you can have a send right or a receive right, and that's rights to send or receive messages to that given port. And basically the main way that these rights are distributed is that any task can send rights for a port to another task. So if you own receive rights on the port, you can create a send right and then send that to another task. And that's just sort of how basically the entire security model works. And so how you do this is you just basically include the port name in a message. And because messages are structured, the kernel will know, oh, this is a port name. That means I need to, identify which port that name refers to in the sending task, and then transfer the specified right to the receiving task and allocate a new name for it in the receiving task so it can refer to the same port. So basically the kernel just does all the magic to make things work. This is a lot like file descriptor passing that you can do on Unix. For instance, like the privilege separation design of OpenSSH and a number of other daemons, those use file descriptor passing. The privileged server will receive the connection, and then it'll actually pass the file descriptor to an underprivileged process, and the Unix kernel kind of, transfers the file descriptor on its behalf. Same kind of mechanism. And to give you an idea of how this is used, there's a thing in OS X called, or in just about any Mach system, called the bootstrap server. So basically, if tasks want to communicate and they don't have a write, there's just no way that they can actually send messages to each other. And so the Bootstrap server is essentially the middleman. And what you do is, like, say you want to create a local RPC service. So task A, or I'll say task X, creates a port and then sends a message to the Bootstrap server with that port saying, I'd like to register an RPC service named foo. And by sending that port to the Bootstrap server is now granted send rights on that port also. So other tasks can send lookup messages to the Bootstrap server, and then basically then the Bootstrap server will send rights, or will transfer send rights to task Y, and then task Y can send messages on that port, and it'll get to task X. So you kind of need this trusted third-party middleman sort of thing to actually work. And this forms basically the entire Mach security model, which is a capability-based system where there's no notion of users or groups. The entire security is based on the capabilities that the communication capabilities, like when you have send or receive rights on these ports. And so one thing to keep in mind is that, if you're kind of playing with local privilege escalation on OS X, your target is basically a task port. So there's ports, they're basically are ports that are held by the kernel, but that refer to each task, and it's called the task port. So if you have access to the task port for like another process or another task, because they're basically the same, they're kind of glommed together, you have full access over it. So I discovered a local privilege escalation a few years ago that was pretty easy. There's a thing called exception ports that I'll talk about later, but basically those weren't cleared when you created a new process. So if you just basically set that port to an exception handler in your process, then you execute a setuid executable, and if it crashes, then basically it transfers port rights to your exception handler, to the task, and then you have full access to the task. And you can read and write memory and then just inject shellcode and run it. And then I found it, kind of liked it, played with it for a while. And then I found that someone else discovered it like probably about the exact same time I did and just left it on a web server somewhere. Because keep in mind, there's never just, bugs aren't discovered by one person. Just a random side rant. Okay, so one of the things that this kind of exploited was that a setuid process has special rights to the BSD part of the kernel, but to the Mach microkernel, it's the same thing. It's just a task, and so there's somewhat like of a disconnect between those systems, and those are a good place to look for vulnerabilities. But basically, the way that the kernel is kind of glued together is that every BSD process in the kernel has an associated Mach task. But it's not necessarily a one-to-one mapping. You can actually create naked tasks that are not Mach processes. You can do kind of a bunch of crazy stuff that will, if you're not careful, will panic your kernel. So, but of course, if you're not a process, you can't execute any BSD system calls because you don't exist. So it's a little fun there. The other thing to keep in mind is that same thing with threads. There are low-level Mach threads, and normally you access them through the POSIX threads API, but a POSIX thread is not identical to the Mach thread. Basically, I call it a naked Mach thread. And if it tries to execute certain functions, it'll fail. And so you need to kind of promote a Mach thread to a POSIX thread. And so in order to bridge kind of the BSD process, like process IDs and Mach tasks, there's these glue system calls, like task for PID and PID for task, which pretty evident what they do. All right, so let's kind of talk a little bit about Mach RPC. So I talked about ports and messages. This is just the basic IPC, just unidirectional inter-process communication. On top of that, Mach has a high-level remote procedure call. And this was kind of really early. Like this stuff came out like, late 80s. I mean, this was kind of one of the first like RPC systems. Uses Mach messages for communication, uses NDR representation, which is the same representation that Microsoft's RPC uses. And basically how it works is you have an interface file that's like it ends in .defs, and you compile that with a thing called MIG, which is the Mach interface generator. This generates all the code for you. This is like RPC Gen for Windows or RPC Gen for Unix. I can't remember what the Windows one is, but same thing. And if you look in like user include Mach, there's a lot of these defs files, and you can see just the interfaces for all the kernel RPC servers, which is kind of fun to browse. And basically, the thing to keep in mind is that almost all of Mach's kernel services are implemented over RPC. So to create a new thread, that's an RPC call, an RPC procedure. To create a new task, RPC procedure. To allocate memory, read memory, write memory, all of this is RPC. This is why Mach is slow, because to do, whereas on a normal kernel, you have to just do a simple trap. A full RPC call for these low-level operations can be a little too heavyweight. And the Mach traps are just very minimal, so it's microkernel. But here's some examples of the kernel level RPC calls that you'll see. Task create, thread create, all this stuff. Basically, the point is, when you're writing kind of low-level code, all the fun system things that you want to do are over Mach RPC. They're not traps. So, with that segue, let's kind of get into some rootkittery. So, why use Mach? Mostly because most of the stuff rootkits that have been demonstrated for OS X are just basically porting Unix techniques over to Mac OS X. And yes, Mac OS X is Unix, and so anything that works on Unix can usually be made to work, pretty straightforwardly on OS X. However, the Mach functionality is more unique and more obscure. So if you're trying to hide on a system, you don't really want to be using the same thing that everyone else is. So if you have kind of a little more obscure, hiding place, well, more likely you're not going to get detected, assuming you don't crash the system. The big risk is, nothing says I'm owned like a kernel panic, in a random place. So you're going to keep that in mind. Also, Mach is fun. Imagine relearning, TCP and Unix and all this stuff all over again, and getting that great, I don't understand what the hell is going on feeling that we've all missed for years. So that's why. So first I'm going to talk about user mode rootkits. And kind of give some backstory. Everyone knows about kernel rootkits. Basically, first there was userland rootkits, just backdoored applications. Then people moved into the kernel, and now kernel stuff is actually pretty easy to detect because you can find the hidden files using like rootkit revealer and a number of other tools that basically look for discrepancies between the files reported by the kernel and stuff on disk. Also, it's very easy to scan the system call table for anything that, any pointers that are kind of not where they expect to be. This stuff is pretty vanilla. And so with user mode, it's actually, you can get remote access through this in a little more difficult way because, way that's a little more difficult to detect because there's very few applications that look for just random code sitting in an application. What are you going to use to find it? There are some defense systems that look for sort of like, process A opening up the memory address space of process B, and that's how they try and prevent it. But once it's already done, it's kind of hard to find. And because it's application specific, it's more custom, harder to scan for. And so the way that you think about this is it's usually based on injecting code in a thread. Just load up, we have direct access to the memory address space, so let's just allocate some memory, inject a thread. Windows has actually a function for this called create remote thread that does it all for you. But Mach was not so nice as to provide this for us, so we actually have to write it ourselves. And it's a little more difficult than you'd expect. And they kind of had the rhetorical question, would you notice just an extra bit of code in a thread running in your web browser? There's like 100 threads in there. You're not going to really see this. So first thing we need to figure out is how do we inject a thread into another process? First, you need access to the task port. That you can get this through task for PID. And the thing to keep in mind is on the default security model for OS X, you can't just call task for PID on an arbitrary process, even if you own the process. So that's one of the areas where the Unix security model and the Mach security model differ. On Windows or any Unix, if you own a process, you can ptrace it, you can get access to its memory. That's not so on OS X. So basically, you need to become root and then execute what's called task for PID. There's an insanely complex security policy for this thing that involves just magic groups called procview and procmod. And actually, when you execute this system call, the kernel does an RPC call. Oh, you should also keep in mind, RPC calls can go to the kernel and from the kernel. So the kernel can talk to a userland server and vice versa. So when you call this task for PID function, it actually makes a RPC, the kernel makes an RPC call to a userland process that gets dynamically started up just so it can tell the kernel what the security policy is for this system call. It's kind of weird. It's called task gate D, if you guys want to play with that. So basically, to inject a thread, we're going to allocate to remote memory. Create remote thread on Windows allocates a stack for us and all this stuff, but we need to do it ourselves. So we need to create some memory for the stack, make a guard page, so if it runs off that stack, it doesn't just start corrupting random memory, and also allocate the code, of course. And there's obviously a Mach call called create thread for this, and create thread just takes the register, like you give it the values of all the registers. You just say start a thread and here are all the register values. So there's definitely some assembly required to actually get it to do something. And so to make this easier, I have to make a trampoline, because also this just creates a Mach thread, not an actual POSIX thread. If you want to call any like Unix functions from it, they're going to get really confused when it's not a POSIX thread. So basically, I had to build a trampoline that's some dynamically injected code that will call other functions that takes a Mach thread and sort of build the structures in memory to make it a valid POSIX thread. I call this promoting a Mach thread to a POSIX thread. So then the next trick is, okay, the thread executes. And basically, it calls the function that we want it to, because we basically built its stack for it, and then it returns and it jumps off the stack to the function. So then, once it's done calling our target function, it just crashes. So, crashing the remote process is not exactly stealthy. So this is where Mach exceptions come in. And so if you kind of look at how exception handling works on various operating systems, Unix is the most primitive. Something happens, signal handler. Windows has structured exception handling, which is a little more complex. Mach takes it another level, and they use actually RPC to handle all this stuff. So, when a thread crashes, basically, there are these things called exception handler ports that are assigned to either the thread or the task. And so basically, the kernel will basically look at if these are set and send messages to these RPC servers saying, hey, this thing crashed. What should I do about it? And what's cool about this is it lets a separate process catch the exceptions in another process. So this is how the OS X crash handler works. Like when something crashes and you see the little pop-up like application is crashed, what do you want to do? Whereas like on Windows, this actually needs to run in the process itself. So it's kind of unreliable. Sometimes you can just, if you're doing exploit development, you can just destroy things so much that this dialog just won't run. On OS X, it runs in a completely separate address space. So it just freezes the process and just pulls the information out that it needs. So it's more reliable. But basically, what we're going to do is we're going to use this to catch the return value of that function. So we set our injector as the exception handler, and we inject a thread, say call function foo. And when it returns from foo, it's going to crash at a known address that we look for. And we say, oh, it crashed. Okay, so that means that the return value is in EAX. Boom, pull it out. And so now we have a little primitive that we can use to just call arbitrary functions in a remote address space and collect the return value. It's kind of cool. So now we can use this to build the tools to inject a full compiled bundle. For those of you who are unfamiliar, a bundle, so the Mach O is the binary executable format for OS X. It creates executables, dilibs, which are like DLLs and shared libraries, and a third type called a bundle, which is a specific linking type for a plugin. So that's what makes these kind of nice to just inject plugins into arbitrary applications. So I use this all over the time, all over the place, all the time. I'll say two things at once. So what we're going to do is we're going to inject a thread, like I mentioned, and then when it returns to a known bad address, that generates the exception, we collect the return address. And so we can use DLOpen. So basically what we can do is we can tell the remote process to call DLOpen to load a bundle from disk, and then that'll give us the handle that we can then pass to DLSym to look up symbols in it and call arbitrary functions in it, and then close it. We can just do this stuff as if the main process is doing it. Alternatively, if we didn't want to actually have the bundle on disk, the OS X linker provides two amazingly useful functions, and they're all a mouthful. NS create object file image from memory, and NS link module. Basically, what you can do is you just write it to memory. If you have like a Mach OS bundle that you want to get loaded, just write it into memory anywhere, and then call create object file image from memory, and that unpacks it, like basically mapping the sections of the file where they need to be in the address space. And then you call link, and it loads up any dependent libraries and everything you need. And so what this lets you do is in your bundles, you can use any framework. You can use write them in C, C++, Objective-C, use any system library, use QuickTime, whatever. What the hell? You can't see this, but my machine just panicked. I didn't even load the rootkit yet. Okay, so while this is rebooting here. Okay, so sweet sound of a Mac. Basically, what this lets us do is write whatever we want. And so I wrote exploit payloads using this as well, and I talked about those a little this morning, some Metasploit payloads that will inject libraries to take pictures with the iSight camera, because QuickTime actually makes all this stuff available, so it's pretty easy just to call these functions, and it just loads up all the stuff that you need. And so I have a tool called inject bundle, which is a simple command line tool that you just give it a process ID and a compiled bundle, and boom, it slams it right in there. And basically what we can do is use that to implement sort of userland rootkit techniques. One of the things that I wrote was what I call SSL spy. Pretty easy once you're in the address space to hook arbitrary functions. And so what SSL spy does is it just hooks the SSL functions for in secure transport, which is kind of the OS X SSL library. And so if you inject this to something like Safari, it'll log all the SSL traffic to disk. Same thing if you inject it into software update, any of these things. I think this actually gets us to demo time. So let me just do that. Do your thing. There we go. All right, let me. Oops. All right. Okay. Try and make this a little bigger. All right. If you can't read it, that's what you get for sitting all the way in the back in a half full room. All right, so let's kind of play with some of these tools here. Desktop. Okay. Okay, so I have a couple bundles here. One is one for iChat, logs all the chats to disk. iSight, which will basically grab grab a single frame from the camera. SSL spy logs all the SSL traffic, and test, which just shows you the life cycle. But to show you how easy these things are to write, let's just bring up basically the code, and you just define the functions, and the convention I use is a function called run. So basically once it's loaded, init will be called implicitly, then I will call run explicitly with a socket if I'm doing this over a payload, and then if it's unloaded, it calls the destructor. And so inject bundle just takes a bundle and a PID, so let's do this. Let's launch Safari. So another thing to point out, the cool thing about doing injected bundles is, so OS X uses code signatures, but very lightly. It basically uses it to make sure that the application hasn't changed on disk. So if you, also for things like accessing the keychain. So basically you put all your passwords into Safari, and then you change it on disk. If the signature is not from the same person, it won't give it access to the keychain items. So if you just try and write your code directly into it, you'll break it. However, if you inject it into memory, you have full access as the application to keychain items. And, well, the only other thing I think they use it for is for parental controls. So if you want to, run that forbidden application that mommy and daddy won't let you write, all you have to do is study up and learn Mach injection. And then you can do it. But, never underestimate the amount of work, a bright kid will go to play that game that requires activation. I think that's why like half of us are here. All right, so launch Safari. Okay. Yeah, it's 293. Oh, no, that's 291. So basically, it just injects it right in there, and I've had kind of Safari running the entire time. Make sure there's nothing. Okay, nothing bad up there. Not to plug. Okay, yeah, I read /dot. Y'all can make fun of me. But basically, the application is still running, and I don't have a connection up. But if I did, and I went to Twitter, basically it would just use my password and log me right in because it doesn't see that the application has changed. And however, it'll just log everything that I do to disk. All right, so let's go back to. Okay. Yeah, so basically the point is, the other thing you can do with this is evade things like little snitch and so on. So did that demo. Okay, so here's the cool part. This is something a rootkit that I call Machiavelli. And this is sort of proof of concept. No, this isn't going to be used to own your grandmother, blah, blah, blah. The version that I'm releasing, while it will, initially I was just going to let it work on localhost, but it will work over the network. However, keep in mind that you have the server you're connecting to has just as much access to you as you do to it. So if you try and use this without changing it, you will get owned. So how this works is Mach used to have this thing called a net message server because the Mach messages are so abstracted that they're actually designed such that they could be sent directly over the network. And they have some optimizations for local message sending. Like if there's a lot of data to be sent, the kernel will just remap the memory page rather than actually send all the data. And so old Mach releases included this thing called the net message server, which is sort of like the RPC bootstrap server, but for the network. You can say, look up this server named foo on this machine. And then it gives you a Mach port back, and you just call RPC on it, does everything. So it basically is RPC like you're used to using it, like for another machine. Most Mach is actually just local machine RPC. And this stuff was taken out of OS X. It's sort of it's historical. What Machiavelli does is add it back. So like I mentioned, Mach RPC gives you all the fun things that you want to play with, like stuff to allocate memory, read and write virtual memory, create threads. Other cool thing is you have all these calls that can be used on any task, which means any userland process, but the kernel is also a task. So you can inject threads into the kernel, you can read and write memory directly to the kernel, all by doing task for PID 0. And also, basically, what things we want to do is we want to reuse all the already generated stubs. So like a lot of the functions that you use in your code, like you call the function VM allocate, that's actually an RPC stub. And the first argument is actually a port. Usually they say it's like a task, but it's actually a port. And so what Machiavelli lets us do is it basically becomes an RPC proxy. So it'll give us a port that we can use all these existing functions with. We just say, instead of using this task port, use this other one, and it will just transparently basically receive the message, wrap it up, send it over the network, and then do the actual RPC on the remote side. And how it does this is by making what's like kind of like an RPC bridge, sort of just like a network bridge, where basically it's like kind of a low-level thing, and it just keeps track of which MAC addresses are on which side. It's like, oh, this is local. If it's not local, send it across. Basically, that's what Machiavelli does, and that's why I said basically you have the same. It has the server you're connecting to has the same amount of access to you as you do to it, because it's basically bridging them. And we have kind of three big components here. We have the proxy, which basically gives you proxy Mach ports to receive the messages, translate them, and then serialize them to a byte buffer to send them across the network. The agent receives them, receives kind of the serialized messages, unwraps them, sends them as an RPC call to a local RPC server, receives the reply, sends it back. And as a little extra glue, we have an RPC server that's just local to the process. And what that means is our entire network protocol is Mach messages back and forth. You don't have other various protocol stuff. We just use serialized RPC messages for everything. And so just use RPC to get the extra, there's an RPC server to give you extra glue, like to provide like the Unix sysctl system call and so on. So here's, every year I try and do something new for my presentations graphically, because left unchecked, I will just do bullet point after bullet point after bullet point. So a few years ago, I started actually doing diagrams. So behold, this will be the first animated diagram that I've ever made. This is a very special time. I hope you all can feel it. All right, so this dotted line here, also you can, hope you all like box and arrow diagrams, because that's all I can do, but I got colors. So on the top is one machine, on the bottom is another machine. So we have the RPC client stub. This is like local generated code. And when you send a Mach message to it, it sends it to the Machiavelli proxy. And so the Mach communication is in blue. So it sends the message to the Machiavelli proxy. The proxy translates it over TCP and basically writes it out, sends it over. Keep in mind that this can be any data channel, because it's just a byte buffer. So for my first implementation, I did TCP just because it's easy. But the Mach API is the same in the kernel and out of the kernel. So this could be an ICMP message that's intercepted at a low level and just injected into the kernel. It could be in a TCP SYN packet. It could even be embedded in a web page, and basically the kernel is looking at data coming in, and it scans it, and it can see like, oh, that's a message. Embed that in there, and then sends it back as a cookie. You can do some crazy stuff with this. So then Machiavelli agent receives it, converts it back to a Mach IPC message, sends it to the RPC server, which then replies, sends it back over TCP, and back over IPC to the client stub, and you get your return value. So behold my animation power. So to give you a little more detail on how the messages work, is we have they're structured. They have just basically think of them as like network packets. You have a to, a from, and then structured data. And the data is not just bytes. It's actually structured, because the kernel has to go through and identify if any of those items in the body refer to a port, and if so, actually transfer it. So it has to have a known structure. And these are called complex messages. A simple message is just bytes, but a complex message has what are called descriptors, which basically means this memory address needs to be, the memory page needs to be transferred. And so to serialize these over the network, you just need to basically say, oh, this pointer is actually a bunch of data we need to actually copy and write out. And the kernel does this so that it can transfer port writes between tasks, like I mentioned earlier, and also can transfer memory pages. You can do crazy things like you can actually specify where the memory will be written to in the target process if the receiver uses a special flag. So those of you looking for local bugs, you might want to look there. So to proxy it, we just have what's called a port set, Mach kind of always makes these handy, they have a different philosophy than Unix. Unix puts a lot of the grunt work on the programmer. If a system call is interrupted, do it again. If you want to listen on a bunch of file descriptors, you need to use pull or select and then figure out which one had a problem. Well, Mach is a little more object-oriented. They say, well, you can, for all of our send and receive calls, you can use a port or what's called a port set. And if you just use a port set, which looks, smells, and tastes like a port, it'll work the same. And it'll just tell you in the message which specific port it came in on. So that's what we use for our proxy. And we be a little creative here because port names can be arbitrary 32-bit numbers, and you can choose them. We just make them that be like a hash table built in. Basically, the port name is a memory address, and you just dereference it to get the destination port. So a little niceness there. Serializing messages is as simple as it sounds. Write it to a buffer. If it's a complex message, then you need to tack that memory pages and other things onto the end. Deserializing, you kind of need to be a little more creative. Like if a port was sent, basically you need to replace the port name that is meaningless on the local side with a proxy port. And the cool thing about this is that means that with Machiavelli, you get access to the first kind of proxied port, and all the communication you do after that gets automatically transparently proxied. So if a RPC call returns a port, basically you can use it without having to do anything special. The subsystem will automatically proxy it and send it in. If memory was, like a memory page was attached to the message, you have to basically map it into the address space and copy it in there. Just kind of do your housekeeping. To give you an example of how this works this is just a simple kind of local utility to just do an RPC call, which gets the page size of the host. And so basically there's like a second paragraph, you can see those 3 lines. It says Machiavelli init, Machiavelli connect, and host self. Those are the only 3 lines that separate this from a normal utility to do it to the local host. For a local utility, instead of calling Machiavelli host self, you just call Mach host self, which gives you the host port for the local system. You do this, you get the host port for the remote system. And then you can just do RPC as you normally would. So this makes it easy to take any utility using the Mach APIs and just say, do it over there. And also means it wouldn't be too hard to actually make like a shared library interposition thing to make this automatic. So you could run one tool and say, run the second tool remotely. But I haven't done that yet. So let's do some demo. And I guess I'm not going to use VMware because that may panic my machine again. All right. Okay, actually, yeah. Let's see how long that takes to start up. Okay, actually, let's give it a minute to boot up the VM, and let's hope it doesn't misbehave here. Sure, yeah. Yeah, that's a good point. So, gentleman mentioned this seems very similar conceptually to the syscall proxying that was introduced here at Black Hat several years ago, and is the basis of penetration testing products like Core Impact and earlier versions of Immunity Canvas. And yes, basically this is kind of a higher level. It's kind of similar. It's analogous. As syscall proxying is to Unix, this is to Mach. Mach RPC is a little higher level, so this is a little higher level. But one of the benefits is that all of Mach RPC is synchronized. So if you're doing like kind of low-level rootkit stuff, you have to be sure not to have race conditions, and not panic the remote system. But basically this kind of, as long as you don't do something really bad, makes it much easier for you because the kernel synchronizes everything. All right, so. I'm going to pull this over so I can actually see what I'm doing for a minute. This is where I start faking the demo, like. Okay, so basically all I did was run the shell script that totally fakes the demo. Basically, my Machiavelli agent implementation is called TCP server because it's just the Machiavelli one that operates over TCP. And what I can do now is grab our client. All right. So here we have a bunch of client utilities. We configure it with some environment variables. Actually, wait, I don't need to be root here. That's why. Okay, so basically, I set the environment variables, and that basically configures it to go to the VM. And I have a small utility here that's basically just local. That's PS. Oh. Why? Yeah, this is why I had the VM fully prepared and all that stuff. Okay. Okay. There we go. Okay, so now this PS, what it did is it did all this through Mach RPC to grab all the process listings and basically did an RPC call to the embedded RPC server to do the sysctl, which gets the process listing and get all that data coming back. Kind of cool, but that's just very small. What's a little more interesting is injecting bundles over the network this way. So I have another version of inject bundle, which this is 4-line change to port it to Machiavelli, and I can inject stuff arbitrarily over the network. So it's okay, let's just use so I have the same bundles there. So let's, I don't know, let's see, directory service, PID 12. That probably uses some SSL. Let's just spy on its SSL. Demo, there, cell spy, and PID 12. So it takes a little longer because it's going over the network. I think I did something to piss off the demo gods royally, because my demo earlier this morning, didn't work either. So I guess you'll all have to download it and try it at home yourselves. I didn't have the projector connected. I don't think it'll affect this, but when I was doing the virtualized rootkits talk here at Black Hat like 2 years ago and demoing my rootkit, it actually didn't work because the memory layout was different when the projector was plugged in. So basically, here we're on the rootkit, kernel panic. That's odd. Try a couple times, and then it worked once I did it without the projector plugged in. Again, so I could fake the demo. Which, if I faked the demos, they'd actually work. So maybe I should start doing that. All right. Okay. All right, so yeah, basically like I mentioned, we have an RPC server to kind of provide some glue, and basically, instead of providing functionality in that daemon, you can also inject the module into any other process. So launch D is basically like init. It's the main process. On OS X, you can very easily inject code into there. Or like I mentioned, write this for the kernel and use what's called the network kernel extension to do that. I've got a few minutes left to talk about some kernel stuff here. So like I mentioned, the Mach API in the kernel is virtually the same as it is in the userland. And most OS X rootkits basically just take Unix-style stuff and port it to OS X. A common technique is to load as a kernel extension and remove itself from the kmod list. So then if you list the list the loaded kernel modules, you're not going to see it, and you're not going to be able to unload it. However, that's pretty easy to spot. And you can also directly load into the kernel with directly writing to the task, just like I did with thread injection. In both cases, there's an unauthorized Mach-O file in the kernel, and that's actually pretty easy to detect. So I wrote a tool called uncloak, and what this does is basically, because the kernel task is available, you can actually just get access to the task by calling task for PID 0, and then enumerate its allocated memory regions. And this would be all allocated memory in the kernel. And then you can just go over it looking for the Mach-O headers that indicate that a binary object is loaded there. And you just have to sidestep some things to avoid kernel panics. For instance, like DMA memory, you don't want to read that. And basically, once you find a Mach-O header, you can look at what segments it refers to, like where it has the text segment or its data segment. And you just compare those to the segments that should be loaded from the kernel module list. And once you do this, this will basically give you, and kind of do a diff of these, you will find any suspicious Mach-O objects that are somehow loaded in the kernel, but aren't either A, the kernel itself, or B, a authorized kernel module. So let's panic my machine again. All right. You can just go away. Okay, so if we run uncloak, obviously, since we're reading kernel memory here, we need to be root. So we run uncloak starting at address 0, and it'll just scan through it all and tell you where it finds Mach-O objects and which segments it actually refers to. So we can actually now use kernel Mach-O dump to dump one of these to disk. So where is my cursor? So, okay, so if we do that, we should have created a Mach-O dump.out, which is a Mach-O object, and we can basically list the sections in it, and of course we have we have all the code there, so we can use this to reverse engineer whatever whatever rootkits on my machine that's actually making all my demos fail. Okay, so like any rootkit stuff is a cat and mouse game. So how do we make a rootkit that'll evade this? Unix system call filtering can't filter the Mach RPC calls that you're doing for this, so you're getting good low-level access from userland. So you can't use a Unix-oriented rootkit to get around this. You need to actually get into the Mach layer. And so what you need to do is filter the in-kernel Mach RPC. And basically, analogous to the Unix system call table, there's also a table called MIG buckets. And this is where the function pointers for all of the in-kernel RPC servers are stored. And so it's a hash table rather than an actual just straight table. So you have to do a little more work to actually find the right place, but it's just a table of structures with function pointers in them like anything else, and you can just overwrite these and actually intercept the basically incoming messages. And you can write your own RPC server and use code like this, which I call inject subsystem, to actually find the right place in the hash table and patch yours in. And so because you have the defs file in the Mach interface files and user include Mach, basically just grab one of those and write your own replacement server. And basically you just tell the interface generator that the code is going to live in the kernel, and then you compile this into a kernel module and load it up. So that lets you do all that. Kind of give you an idea of what functionality you can play with here. This is just a list of the subsystems. Subsystems are just a collection of RPC routines. Subsystems that are in the kernel. The VMs, ports, all this Mach stuff. There's like some other cool fun ones like the default pager object lets you interact with like how memory pages are swapped out to disk, and UND reply. So like when the kernel wants to pop up a message on your screen, there's this thing called the user notification daemon that gets an RPC message. This is how you reply to it. That's also a good way to run commands as root. So if you have, I don't know, a way to do Mach RPC remotely, you can just call that, execute commands as root without having to create a shell. So I think basically it's been about an hour. So in conclusion, Mach is a whole lot of fun. Because of like the flexibility of the system, we can actually tunnel a lot of the stuff over the network cleanly and avoid locking issues and things like that. Keep in mind though that although the iPhone OS shares a lot of the architecture with the OS X kernel, they've actually hardened the kernel, so a lot of the stuff isn't possible. And those knobs actually do exist on OS X as well. You can set a sysctl called I think it's called secure kernel, and that'll actually block a lot of this stuff. So that's some stuff to play with to make sure your system isn't laughably insecure. For the updated slides, go to my blog at trailofbits.com, and I'll have the slides, and once I figure out where the demo failed, the tools that actually work there, and a little README, so you guys can play with this. Again, keep in mind this is not a ready to go rootkit to go own up Apple fanboys, but it's a kind of proof of concept of a interesting technique to use for rootkits or other kind of remote tools. All right, if you have any questions? Yeah, in the back. One more time? The question was, all things considered, would I still rather use a Mac OS than a Windows OS? I mean, I think it's kind of obvious. I've used Mac OS X exclusively on my systems for, I don't know, about almost 10 years now, and I haven't been publicly owned yet. Knock on wood. So, yes. So the question was, if I'm talking to non-technical consumers, what would I warn them about with Mac security issues? Basically, it's the same advice that I give to like my parents or my non-technical friends. In my professional opinion, running a Mac for the average person is safer than running a Windows machine because there are less threats against it currently. However, as Apple gets more market share, that may change, and so you should keep your eye out for when that that time is needed. I don't run antivirus. I don't think it's really going to do anything for me because anyone that's trying to own me is going to evade the antivirus anyway. So don't really care. Yes, Charlie. Yeah, so the first question is, do I need to, with the remote bundle injection, I don't need to load it from, I don't need to copy the disk over or anything like that. The answer is yeah, no, I don't. You can use, well, actually, that's why the demo didn't work. I didn't actually port it to use the load object from memory. Basically, when you're doing it locally, you can basically call dlopen and all that stuff to load the bundle from disk. When you're doing it remotely, you just write it to memory using VM allocate and VM write, and then call the ns create object file from memory and all this stuff so that the bundle never hits the disk on the remote system. And for added fun, if you're using this in the wild, basically the rootkit itself can be made to be a bundle that's injected. So basically it could never hit the disk, and it just gets loaded as a bundle and a background thread in an arbitrary application. That's kind of all like the finer points of actually using this for a full system, but I did the mechanism and I stopped there. I'm not interested in doing more. And the second question from Charlie was, oh, do I need to load a driver? For this version, no, because it's all in userland. So it all uses the Mach function calls. And so basically say you have an exploit and a local root privilege escalation, and then you run this thing as root in the background or inject it into another process as root. No drivers necessary. You're not doing anything in the kernel. But because the RPC lets you interact with the kernel as root, you have full kernel interaction from this, and you can even use this to load drivers into the kernel. Yes, over there. I haven't looked at Snow Leopard at all because of the NDA. Because I'm up here talking about things, it's easier just to never look at it. So I've heard Apple is focusing on security on it, and I eagerly await looking at it. Yes, sir. Yeah. So the question is, with the remote exception catching, it seems odd that there's no process that handles exceptions and all the processes on the system. I mean, but that's actually what it is. There's a daemon called crash reporter D in earlier versions, which became report crash D. And what that is that's the background daemon that when a crash happens, it gets a message and then it displays the dialog to you. So it's basically, because the exceptions sort of percolate up, so if there's an exception handler for the thread, it goes to that. If there's one for the task, it goes to that. And so whenever a new task is created, its exception handler port is initialized with the port of crash reporter D, so that the crash message basically goes up to it, and it can do whatever it needs to. So if you're fuzzing, you can use that to monitor crashes system-wide too. That's correct. I changed the remote processes designated exception handler to be my own Mach port, so that instead of going to the local crash reporter and providing a notification that it crashed, I catch the exception, and then the RPC message is sent over the network to my local system, where I can collect the return value locally, and then I tell it to terminate the thread, just stop execution of it. Yes, sir, in the shirt over there. Well, so my demo presupposes basically that you have root already. There's, once you have admin access, like access as an administrative user, root is trivial to obtain after that. And if, in other cases, it requires a privilege escalation. And largely, Macs are considered single user systems at the shell level, so it's not the most hardened attack surface. Yes, sir. DYLD insert libraries. Yeah, so the OS X linker has what's called a two-level namespace. And so when you try and do like an insert library, so the two-level namespace means that there's like a namespace for resolving things in the local module, and then a global namespace. when you try and use DYLD insert libraries like to hook malloc or something like that, in C++ it'll often fail. So what you need to do is you need to do DYLD force flat namespace. And what that'll do is that'll force it to be flat. However, that sometimes breaks applications. So if DYLD force flat namespace works, doing the insert, DYLD insert, whatever, will actually work there as well. However, basically, because of my bundle injection stuff and hooking manually, I mean, I wrote this stuff so I could do that too. So you can inject at load time or just inject dynamically and patch the functions, the actual functions in memory to hook them. So if that's what you're trying to do, that's another way to do it. All right, I think that's all the questions. All right, enjoy your lunch. If there's any other questions, just hunt me down.